All right, so real quickly, let's talk about the isotopes. Okay, so isotopes, we learned when we did the build an atom FET that the protons dictate whether an element is one thing or another. So one proton will always be hydrogen. However, there's different numbers of neutrons that can exist with that proton. There could be none, or one, or two, and each of those neutrons will change the mass. So all three of these atoms would be recognized as hydrogen because they only have one proton. The difference is the mass because of how many neutrons are there. So these are called isotopes. So they react the same, or at least in similar fashion, but they could have different properties. Like tritium here, the hydrogen with two neutrons and one proton. This is radioactive because this nucleus is unstable. So here are some examples of the mass number notation, right? Magnesium 26 is magnesium that has a mass of 26. That 26 is telling you the mass because magnesium is already telling you how many protons it has. So that is 12 protons because all magnesium has 12 protons, and then the neutrons must be 14, which is the mass minus 12. Electrons will assume it's a neutral atom unless there's a charge. Chlorine 34 is an atom of chlorine that has 17 protons, and then 34 minus 17 neutrons, and therefore 17 electrons. All right, we did all this already. Okay, is carbon 12 versus carbon 14, which of these are these isotopes or different atoms? Carbon 12 and carbon 14 are both the same element, therefore they are isotopes. They have the same number of protons. It's the neutrons that makes them different, and therefore these are isotopes. They will behave in similar fashion because of their protons being the same. Boron 11 and carbon 11, are those isotopes? No, those can't be isotopes because they are different elements. They have different protons. They will react entirely differently, even though they have the same overall mass. Okay, so let's talk about radioactivity and its isotopes. This is sort of back of the test type questions. When we were building these atoms, we noticed that there was a potential to put neutrons in so that the atom was unstable. Here's a carbon unstable atom, so the nucleus would have been shaking around. This is carbon 14, so it has the 6 protons and 8 neutrons. We use that in industry when I was working in industry, because then anything with carbon on it, if you enrich your carbon so that it was the radioactive type, the carbon 14, you could then follow that carbon where it went. It was very useful in medicinal purposes because then we could give medicine labeled with this radioactive carbon to mice or whatever and follow where that medicine goes. The experiment I explained in class had to do with scientists putting bags over trees and then filling that bag with radioactive carbon dioxide, so CO2 with enriched C14 present so that it would show radioactivity. And you all realize that carbon dioxide goes into plants so that it can make its food and release oxygen. Well, the oxygen, if the carbon dioxide was, so here's carbon dioxide, right? So if the carbon is radioactive, when the plant takes in the carbon dioxide and releases oxygen, the oxygen is not radioactive, only the carbon is, and the carbon stays with the plant. So the question these scientists had was, are these plants sharing their resources with each other in their underground roots, or do they share just with like plants? Do oak trees only share with oak trees and not with pine trees? So that's why they ran this experiment. So they enriched the carbon dioxide for one plant with this radioactivity, and they figured if they found elevated levels of radioactivity in certain plants, they would know they had to get them that radioactivity from this one plant that they exposed to the radioactive carbon dioxide. And what they found is that all the plants in the forest had increased radioactivity, somewhat certainly implying, if not proving, that the carbon being exchanged underground was for all plants and not just for a certain plant, and that the roots don't serve a purpose just for one plant getting water. It's actually serving to help the rest of the forest get the nutrients they need, which was an interesting thing. Okay, this brought up the idea of a half-life, and this is why we had popcorn. Any isotope that is radioactive has a half-life, and a half-life is the amount of time it takes for half of it to go away. So if you had 1,000 atoms of a radioactive isotope like C14, how long would it take for you to have 500 atoms of it? And how long would it take then to have 250 atoms of it? And then 125. So these jumps would happen in what's called a half-life amount of time. And the reason we use popcorn is you can kind of think of the popcorn kernel as a radioactive isotope, right? If you have a popcorn kernel versus a normal corn kernel, this can become something else, right? Whereas the normal corn kernel, it just gets hot when you heat it up. This popcorn can become something different, and that's because it's a little unstable, and that it can become something more stable, right? If you put this in heat, it actually releases energy, just like a radioactive atom might. So when we were cooking popcorn, the point where half of it was popped and half of it was not would be considered the half-life. So half of these kernels have popped already and half of them have not, and we would consider that the half-life. So however long that took would get, so if we had 1,000 popcorn kernels, the point where there's only 500 popcorn kernels left and the rest would be the fluffy white stuff, that would be the half-life of popcorn. Okay, so here are some half-lives, half-lives, I guess. For some common elements, uranium-235 is used to power plant for power plant energy. It takes 704 million years for half of the uranium-235 atoms to become something more stable. Carbon-14, it takes 5730 years. And that's how we use it for fossil age. If you ever heard of carbon dating, if you're eating carbon things, which we all are, if it's plants or beef or whatever it is, we're replenishing the carbon-14 in our body, and everybody's body has a certain percentage of carbon-14 in it. Well, if you stop eating, then you're no longer replenishing your carbon-14, and then as it's radioactive, it'll start decaying and becoming other things. So in 5,730 years, your carbon-14 level would be half of what it used to be. And then in another 5,730 years, it would be a quarter of what it used to be, and so forth. So that's how they can determine the fossil age based on how much carbon-14 is left in it. Now, the problem is, you can see here, you would run out of years after, maybe about 20,000 years, your carbon-14 might get to a point where it's not as detectable, and zero is going to be zero for a long time after that. Hydrogen-3, which is tritium, takes 12.3 years. So you can see here there's basically different days that different atoms that are radioactive will take time. So we talked about that some, and that's all I'm going to talk about right now. Thanks for listening.